In this video, I'm going to do some additional examples of hypothesis testing on the calculator. I'm taking some problems from section 10.5, and I would invite you to join me there in the book. In particular, I'm looking at page 565. Now, if you look through section 10.5, you'll see that we're back to the chi-squared distribution. The last time we worked with that was back in section 9.4. And unfortunately, the level of support that the calculator provides isn't quite the same as we're used to having with other distributions. So these tests are actually kind of half on the calculator, half off the calculator. And it sort of depends on what approach you take. We still have two choices. We can do the classic method, which involves the rejection region, or we can do the p-value method. Now, the problem that I want to use as my first example is from page 565 here. It's number 12. And I'll show you both methods for this problem. Number 12 says, counting carbs, the manufacturer of processed deli meats reports that the standard deviation of the number of carbohydrates in smoked turkey breast is 0.5 grams per 2-ounce serving. A dietitian does not believe the manufacturer and randomly selects 18 2-ounce servings of the smoked turkey breast and determines the number of carbohydrates per serving. The standard deviation of the number of carbs is computed to be 0.62 grams per serving. Is there sufficient evidence to indicate that the standard deviation is not 0.5 grams per serving at the alpha is 0.05 level of significance? A normal probability plot indicates that the number of carbohydrates per serving is normally distributed. I think the first thing we want to do, regardless of what approach we're using, whether it's classic or p-value, is figure out what are we testing here? And I think the key sentence in the problem is the one that says, is there sufficient evidence to indicate that the standard deviation is not 0.5 grams per serving? That's your alternative hypothesis right there. So to be specific, the alternative hypothesis is sigma not equal to 0.5. And the null would be sigma equals 0.5. So this is a two-tailed test. Now when you do a two-tailed test by hand like this, using the classic method, you have to find the boundary values of the rejection region. And because it's two-tailed, there's going to be two of them. There's one for the left tail and one for the right. And so to get those boundary values, you have to go digging around in the chi-squared table. So you have to know, what's the area of each of the tails. So you take alpha, which is 0.05, and you split it in half. And the left tail would be 0.025, and the right tail would be 0.025. And so if you go back to the chi-squared table and you find the right row, 17 degrees of freedom, you'll find that chi-squared left would be 7.564. That's your boundary value for the left tail rejection region. And chi-squared right would be 30.191. That's your boundary for the right-tailed rejection region. So you probably want to draw a picture of the distribution and label everything and so on and so forth. The first thing that we need the calculator for would be to calculate the test statistic. And so that would be the degrees of freedom, which would be 17. And then we multiply that by the formula you see there when you look at the test statistic. I prefer to actually calculate it a little differently than the book shows. It's just easier this way. If you know the laws of exponents, you know that this is true. So what I do is I take my sample standard deviation, which is 0.62, and I divide it by sigma naught, which in this case is 0.5. And instead of squaring each individually, I just square the quotient. Makes it easy. So there's my test statistic right there. And if we're looking at this from the classic perspective, you can see that that test statistic doesn't fall inside the rejection region. And so our conclusion would be that we can't reject the null. The evidence that we have is not sufficient to suggest that the standard deviation of the carbohydrates per serving is something other than 0.5. Now, if you want to do the p-value method, you don't have to go digging around in the chi-squared table. That's probably the best part of it, or the best feature of the p-value method. But you do have to know the syntax for the chi-squared distribution CDF command on the calculator here. So in order to calculate my p-value, here's what I need to do. You got to remember, when you do a two-tailed test and you get that p-value by hand, you have to double it. You see, you split alpha between the two tails, right? So the p-value is also split between the two tails. So you have to double that tail area in order to get the correct value. So here's the way you can get the p-value easily. You take 2 times, and you go to the distributions menu. And number 8 is actually the one we want, but I'll go down there so you can see what it is. It's the chi-squared CDF, the cumulative distribution function. It's right there, number 8. So I'll just press number 8. And the argument that this function is expecting is a lower bound, comma, upper bound, comma, degrees of freedom. You can find that in the manual for the calculator. So in this case, we're looking at a right-tailed area, and that means that the lower bound would be our test statistic. So I'm just going to cheat, and instead of retyping it, I'll just use the answer memory register for that. You know that whenever you do a calculation, the most recent result is always stored automatically in the answer memory register. So might as well take advantage of that. The right or the upper bound would be positive infinity. So I'll just put in 1 times 10 to the 99. And the degrees of freedom would be 17. And so there's our the arguments that we need for the chi-squared CDF, and right there's our p-value. So as you can see, the p-value, 0.14 and some change, is larger than alpha. And so on that basis, we would also be unable to reject the null. The evidence we have is not strong enough to suggest, or does not permit us to conclude, that the standard deviation is other than 0.5. Now the next problem that I want to do as an example here is number 14. And it's a data-driven problem, but really the only thing we need from the data is the sample standard deviation. So let me read the problem. It says, number 14, acid rain. In problem 24 from section 10.2, we tested a hypothesis regarding the mean amount of acidity in rainwater in the Columbia River Gorge in Washington. To test this hypothesis, we verified that the data are normally distributed, and we assumed that sigma was 0.27. Test this assumption at the alpha equals 0.05 level of significance. Now if you go back to the section here and you read about the 3 different kinds of tests we can do, you'll realize that none of them permit us to test the claim that sigma is equal to 0.5 directly. That's a null hypothesis. In fact, you'll notice that the null hypothesis is always a claim of equality. And the hypothesis testing procedure is not, logically you cannot test the truth of the null hypothesis, because the truth is assumed as part of the process. So we can't test that claim directly, but what we can test is the related alternative hypothesis, which would be another two-tailed test. So to be specific, the hypotheses for this problem are as follows. The null hypothesis is that sigma equals 0.27, and the alternative hypothesis is that sigma is not equal to 0.27. Now to test this, again, we have 2 approaches. We can take classic approach with the rejection region, or we can go with the p-value. Either way, we have to calculate the test statistic, so let's do that. I'm going to need the sample standard deviation here. So let's go back to the stat menu. And by the way, you can see that as usual, I've keyed in the data already, so I don't have to take the time to do that. So I need the sample standard deviation. I'll go to the calc menu here, and I'll just do one variable stats, and it defaults to list 1. So S sub x is what I need right there. Now, I don't want to retype that number, but it's stored in the calculator's memory register, the one that's called S sub x. So I'll just fetch that when I do the test statistic. Now in this case, if you'll notice, how many data observations do we have? It looks like we have 16. So that means we'd have 15 degrees of freedom, and our test statistic would be as follows. It's going to be 15 times the quotient of S sub x. So I'll get that as follows. Go to the vars menu. I'll go to number 5. And right there, number 3 is S sub x. So I'll just take that, and I'll divide that by 0.27. And I'll square the quotient. Or, well, I keyed that wrong there. Unfortunately, I got to rekey that. So it's 15 times S sub x, vars menu, number 5, number 3, divided by 0.27 quantity squared. So there's my test statistic right there. Now, if you are using the classic approach, again, you have to go back to the chi-squared table. Alpha is given here as 0.05, so we're doing the same thing we did for the last example. It's a two-tailed, two-tailed rejection region, and we're even looking in the same columns of the table. It's just a different row because we have 15 degrees of freedom. So the values would be 6.262. Again, 6.262 for chi-squared left. That's the boundary of the left rejection region, and 27.488 for chi-squared right. Now again, you can see here that this test statistic is too small. It doesn't fall inside either of the rejection regions. And so for that reason, we cannot reject the null. Now again, if you wanted to do this using the p-value, you could do it as follows. You would have to double that tail area, so you would take 2 times, and you go back to the distributions menu. Number 8 is the chi-squared CDF. And again, this would be a right tail because the test statistic is closer to the right value than it is to the left value. So go with that. Or well, let's think about that. Yeah, it's a right tail. So let's calculate that region's area there. We can use the answer memory register again. Ooh, don't want that. Let's try that again here. So I'm going to take 2 times chi-squared CDF, and I want second answer. I keyed the wrong thing there. And again, we'll go with positive infinity. And the degrees of freedom was 15. There's your p-value right there. It's huge. So again, that just confirms it's bigger than alpha, and that means we can't reject the null. So anyway, I hope that helps. And we have one more video here, which is not examples so much, but anyway, it's just designed to help you deal with hypothesis testing in Chapter 10.